Great, so I'm Ted Wilmes. I work for a company called Wellaware. We provide a SaaS solution for monitoring oil and gas wells. So if you have an oil and gas well, you can talk to me afterwards. But if not, we're going to talk about IoT in general today. So this isn't specifically about what I do. I'm going to first cover a little bit about the graph property model, a little bit about Titan database, not too much. Then I'm going to really focus, though, on modeling the Internet of Things in a graph database. My main goal for that piece is to get you guys excited to go try this out on your own. So I'm not saying this is the way to do it, but kind of get that imagination going. It's easy to install Titan, set it up, create your own little application, and try it out. Lastly, because time series data is a big part of IoT applications, why not try to store your time series data in Titan database? Might as well try it out. So I'm going to use that to discuss how Titan actually interfaces with Cassandra, because it is the Cassandra conference, and then also discuss one approach for storing time series data in Cassandra in a performant manner. Okay, so first of all, the property graph model. You may have heard of RDF graphs, so there's also property graphs. So first, we have a vertex. The vertex has a label, so that's basically just the typing information. You can have an arbitrary number of key value pair properties on there, key simply being a string, value being any sort of type that your graph database can support. We add another vertex, and then we add in the other main component, which is an edge, as you probably already guessed. But the edge has a direction, goes from Ted to George. There's a label on there typing that edge. And then again, you can assign an arbitrary number of properties to that edge. So how do we query this? There is an Apache project called Apache Tinkerpop that has defined a standard for folks and vendors to follow so that they can implement this standard graph query language called Gremlin. So really simply, won't go into too much detail here, but just to give you guys a basic idea of what it looks like, we'll do a very simple query against that exact same model I just showed you. So I'm going to say, hey, here, take my graph. Out of all the vertices, I'm particularly interested in the ones that are of type person, and I want to filter on the name Ted. So as you'd imagine, that's going to give you your first vertex, Ted. Think of that as kind of your first step. You're diving into the graph, and then from that point, you may want to, most likely, use that graph, use the edges, traverse out, do interesting things. So we say out, I want to go outbound on the outbound edges that have a nose label, and then I want to return the name of all those vertices that are outbound from that vertex, Ted. So real simple, there's just one, George. Not too exciting, but really straightforward to use, really straightforward to put together some very interesting sorts of queries. So TitanDB. TitanDB is a graph database, open source graph database that has support for pluggable storage layers. Of course, we're going to talk about Cassandra today. It was designed from the ground up for an OLTP type workload, but now there's also really good options for doing more OLAP type global graph computations with it. As I mentioned, it implements this Tinkerpop 3 API in the latest Titan 1.0 version. And again, because it's the Cassandra conference, Cassandra is an excellent option, of course, for the storage layer. We'll get a bit into how that data is stored, and I'll explain that some more in a little bit. So the Internet of Things, well, that's kind of a sort of nebulous topic, but let's just sort of put some loose bounds around this and then discuss an example. So first, of course, we have things. We have some component of time, probably. Maybe we're tracking these things through time. We're getting sensor readings. But people come into play, so we may have users that we're tracking in the system, organizations, places, all sorts of things. So even though we say Internet of Things, to really get meaning out of a lot of this data, there are connections to these other things that we sometimes forget about. The graph database is great for capturing those relationships. So as I mentioned, I'm in the oil and gas, but you may or may not have interest in that, so I decided to come up with a just simple example. So Internet of Things in space. So let's say we're setting up an application to monitor a wide variety of things floating around in space, spaceships, rockets, satellites, all your sorts of usual space things. So as we dive in, we have a rocket here. So let's look at what we could do in the graph. So let's start out here. We have a rocket in the center there. The rocket is not an island. It actually has all sorts of other pieces of information that you can hook up to it to gain context and draw meaning out of it. So first over here, we have the world's smallest David Bowie, Major Tom. He pilots the rocket right there. As I mentioned, there's probably some organizational component, like who actually owns or operates this rocket. So Starfleet. Acme Rockets builds a particular type of rocket called the Delta Booster. So that rocket, you can see there's an outbound edge. You'll notice a lot of times you label those edges with a verb. So that rocket is model Delta Booster. And then we have an engineer that maintains this rocket, Joyce. So you notice that with all of these connections, as you build out your application, you can make use of these connections to do interesting analytics and grab other contextual information about these pieces of data, these things that are in the graph. Okay, so what if we look at the rocket itself? So a lot of times, a thing is actually really a system of systems, or maybe other things connected to each other, and maybe you're just thinking of it at a higher level. So on the left, we just have a really generic exploded diagram of a rocket. On the right, we have a simple subgraph showing, okay, what is this rocket actually made up of? So depending on my role in this organization, I may only care about this thing in the context of it being a rocket. But if I'm actually Joyce, the engineer, I want to do something with this rocket, I care about the lowest level nitty-gritty piece. The graph database allows you to very easily put together these sorts of hierarchies. And also, most importantly, right here, everything's shown as a hierarchy, but a lot of times there's interconnections, dependencies that you can capture in this graph between these different things and exploit those. Simple example would be if you have an alarming system and you're doing maybe some sort of root cause analysis. If I'm an outsider, I'm new to this system, it has many parts to it, maybe I don't understand how everything's put together, you can have something like this model of that system in your graph database and run queries against it to better understand, okay, what is the actual root cause of this problem or the things that came into play. So if we zoom in a little bit further, this is one of those components in the rocket. So these are the guidance electronics. Notice we have our JVM up on the rocket, and unfortunately, it looks like there's a garbage collection issue here. But so we have the JVM, we're moving down to even a lower level. So now we're finally down in that, say, sensor type level, where you're actually gathering some sort of metrics. So we're going to zoom in there and discuss just basically an alarm scenario. So this is just one idea of how you could possibly model alarms. So say you're interested in heap usage, you want to be notified when something goes wrong. So we create an alarm vertex, and that points to the heap usage. That alarm could go off and say, I'm going to notify any number of people. So we just have that Joyce node or maybe some other engineer vertices, hook those up, and then some arbitrary number of alarm conditions. So it's a very flexible way to model these sorts of things. Now we bring in the organizational and the other personnel component. We can tie this back. So what if Joyce doesn't answer her space pager or something like that? So we can just fail over and say, oh, I'll just use the organizational structure that I've stored in this system to figure out I need to actually report this up the chain. So in summary, things can be, depending on your application, but in many cases, and at least specifically in our oil and gas use case, a lot of times that thing can be broken down into other parts, or potentially those parts that you already have can be brought together with some sort of structure and relationships that tie them together. So depending on what you want to do, maybe the higher fidelity of the model that you're actually storing in your system, the more flexibility you'll have. So you can, of course, you could store this same sort of structure in a relational database, but the graph database and specifically the Gremlin language make it that much easier to work with. Okay, so can't talk about Internet of Things without maybe some time series stuff. So now I'll get into the time series and performance information. So we'll go back and we'll build upon this example. specifically looking at modeling how we would store this time series data in a highly performant manner in Titan. Okay, so some really basic nebulous time series requirements, but at least to kick us off. So say we want to support a large volume of low latency writes, and then we want to retrieve primarily the most recent data. That's pretty straightforward. So here's kind of a laundry list of things you would like to look at if you're doing performance tuning or optimization on your Titan system. So one, some of these are probably pretty obvious, but Titan deployment, topology, and configuration, all your usual Cassandra tuning tips and tricks. If you think about it, Titan's running on top of Cassandra, so it's optimizing your Cassandra setup is probably a good thing. Titan JVM tuning, Titan actually runs in the JVM, so usual JVM tuning matters there. Data modeling choices, and then indexing. Titan has its own built-in indexing and can use third-party indexers, so that makes a difference. And then also Titan has a number of different layers of caching that are important. Specifically, we're going to talk about deployment topology and data modeling. Okay, so deployment options, just to beat the space thing into the ground, we have our AWS Mars North 1 region. How could we deploy our Titan and Cassandra? Okay, so here we're looking at just an individual instance. So here on the same instance, we could do a local deployment. So we have our Cassandra running in a JVM, and we have Titan running in another JVM. They're communicating over a socket connection. Okay, so that's one way to do it. We could run it embedded. So Titan could be running in the same JVM as Cassandra. Third option, we could actually run Titan remote. So you could have maybe Titan running in a Docker container, and then you have your Cassandra cluster over here, and they're communicating that way. So if you dive in and actually look at Titan itself, okay, graph database, how do I actually communicate with this thing? You know, how am I going to make an application with it? So first option is the Apache Tinkerpot project has a Gremlin server. So this allows for remote access into your graph database. That could be with a JVM-based language, a REST-type interface, or another sort of driver for a different language. So that's one way to do it. Another option is to actually embed Titan within your application. So for example, we use Drop Wizard, but you could do a Spring Boot setup, Spring setup, you know, whatever sort of framework you're comfortable with. In that case, your application and Titan are going to be running in the same JVM. Okay, zoom out a little bit here. What does that actually look like? Here's an option. Say you have two Drop Wizard containers. You have your Cassandra cluster, and then this is greatly simplified, but then some magic happens and your clients are hitting your APIs. So just to give you just a rough idea of a possible deployment strategy. Okay, so time series. Let's jump over real quick and just look at kind of this canonical time series example with CQL. So I took this off the DataStax Academy website. And so here's a very straightforward and kind of standard way that one could model time series, say storing sensor readings in using CQL. And so I bring this up to compare and contrast with how we're going to do that in Titan. So now if we look at how Titan actually stores data in Cassandra, we have each partition. So Titan makes a number of different column families, but we'll be specifically looking at the edge store. Each partition is going to be a vertex. So you're going to have a vertex ID, and then, and I should say that Titan still uses thrift. So then you're going to have a series of properties that are associated with that vertex. Each one's going to be in a separate column. And then your edges, this is stored in an adjacency list format. So your edges will be stored with that vertex. And they're going to be stored on both sides of that walk. If you think about it, you have vertex A, you have vertex B, you have an edge between. That edge is actually going to be duplicated to both of those vertices in most cases. And so why is Cassandra great for this? Well, one thing that Titan is awesome at is doing edge queries, so filtering by edges. Remember I said you can put properties on edges? And so because of Cassandra's support for these wide rows and the ability to slice that row, you can actually do very efficient edge queries and kind of narrow down onto what you're looking for. I should also say, yeah, down on the bottom you can see how the edge is actually stored, but suffice to say the properties on that edge are stored with the edge. That's the important thing to remember, along with the fact that the edges using the Titan schema system can be set up so that you're ordering by a particular one of those properties, one or more. Okay, so how could we actually store time series data in here? Well, one thing that we could do is say on the top we have our sensor, maybe that we're pulling data back from our metrics. So we have heap usage. And then I'm going to break this data up. We know that Cassandra can handle wide rows, but not infinitely wide rows. So we need to break this up somehow. So I've just created this notion of chunks. It's just think about it, buckets, same idea. And so we have some time range that's going to go in each chunk. Then you could have these observation vertices that you'll hang off the chunks. Those observation vertices will have the timestamp and the value, or whatever other sort of information that you'd like to store with each of those observations. So that looks pretty good. You could imagine maybe doing a year, month, day hierarchy, storing roll-ups in there, things like that. So you could do something along those lines. So that's good, but each one of those vertices, as I mentioned, is a separate partition. So say you're pulling back 1,000 different observations. Well, in that case, if it's down on the observation vertex, you're actually going to have to retrieve 1,000 different observations. So you can imagine that that quickly gets you into trouble and doesn't scale very well. So what could we do about that? Okay, so one thing that we can do is move all those observation properties up to the edge. So maybe we still leave them on the observation, but we also move them up to the edge. So then what we can do is have Titan just perform an edge query, retrieve those edges in a similar manner if you were performing that query with, say, CQL, where it's just looking at, say, a single partition, or maybe if you cross partitions, maybe 2 or 3, depending on how much data you're retrieving. But it can do that slice query and pull them back. The other thing to throw on top of it is you could even skip hanging that observation off the end of that, off of that edge, and instead you could point that edge back to the chunk, because you really just care potentially about that data that's stored on the edge itself. Now, that's good in some cases, but in other cases, you may want to exploit the fact that you can tie things together in the graph. Maybe you want to go back and actually associate something else with that observation, do some sort of tagging, something along those lines. So it's going to depend on exactly what your use case is. If you just need to actually store that raw, say, sensor reading, you're not going to do anything with it afterwards other than just read it back as it is, then maybe you can just leave it where it's just storing it on the edge. What that actually looks like then, if you look at the partition, is we have our vertex ID, like I mentioned. You have your properties that are associated with that vertex, and then the columns simply are just your individual observations. So this looks fairly similar to how it would be stored in the CQL case. There's differences, but it's exploiting the same fact that you're doing maybe not always sequential I/O to retrieve that on your slice query. You may have to go across multiple SS tables, but it's better than hopping around and getting all of those disparate vertices. Really simple Gremlin examples here. Gremlin also actually works really well for querying this sort of data. So in our simple example, let's just say we have one chunk we're dealing with. We're going to say, I'm going to go out the out edge, out E instead of out, so I'm just interested in the edges. I want the specific one with that timestamp, or I could do a between type query, or if I want to do the most recent observation before and now, I can go out E, has timestamp, say now, and then specify an order, and then limit by 1. And so Titan and behind the scenes Cassandra is just going to go and get that single record back. Now, that works really well, but of course you could wrap this up in your own time series API, and that's kind of how we use that as something that is specifically looks nice for dealing with the time series. Okay, so pros and cons. So pros, I mean, and this can probably get into religious debates, but this allows for a single unified view of your IoT data. So you actually have all that first part of the talk sitting in there with your time series data. Admittedly, could be a good or bad thing, so I'm not going to pass judgment on that. Gremlin works well for processing streams of time series data. Cons, of course, the storage format's not going to, potentially is not going to be quite as compact. because Titan's putting some other metadata in there with your information. There's some extra properties on the partitions and things like that. So it may not be quite as compact, although they do some very efficient serialization of that data out themselves. So it may not be a huge difference, but that could affect performance potentially. Lastly, and this is the one that actually requires some managing, some overhead on the developer side, at least when you're making this time series type library, is there's this extra overhead of managing these chunks. So it's not like in CQL where you could just say, insert this new point. Okay, well, if that happens needing to go in a new partition or something, it just happens for you. In this case, especially if you want this to operate in an environment where you're having a ton of different threads potentially running in the same time series, you need something to actually go in and create that chunk vertex ahead of time. Okay, so now I'll briefly talk about how does Titan actually communicate with Cassandra and what are some things that we can tweak to get high performance out of it, specifically just for this time series model, but it's also applicable to other instances. So let's look at a really simple query here. Here I'm saying g.v4. You can look up a vertex by an ID, so I just magically knew that ID 4. That's one of those chunk vertices. I'm going to say out the has chunk edge, and I just want to get the start times for that chunk, so you can just see them there. So pretty simple query. So first of all, what happens when you say get vertex by ID? And this is true whether or not Titan is running embedded, local, remote. The difference here is going to be what's the magnitude of that latency, that communication time that's happening between Titan and Cassandra. So first of all, it says, Titan says, does this vertex exist? So it looks it up in Cassandra. Cassandra said, yep, that's there. So now it has the vertex loaded into Titan's transaction cache. So Titan maintains its own transaction cache. So a brief aside, if you are curious and want to like nerd out on this stuff like I enjoy doing, one good way to just very easily look at this is if you use a profiler that has socket trace profiling, makes it really trivial to look and see what communication patterns look like. So you can go in and even dive in and get a nice stack trace and see where I/O is being started from in your application. Okay, so now we want to say, let's retrieve the properties for this vertex 4, sensor type, and then a units. So it goes out. Remember I said it just retrieved the vertex before. It didn't actually get any properties at the same time. So it retrieved the properties, got back 2 properties. Now those properties are loaded in the transaction cache. So if you use that same vertex somewhere else in that same transaction, Titan's going to hit its transaction cache. It won't go out again and re-retrieve it. So that's good, but you can get an idea here of how, depending on the number of vertices that you're dealing with, properties and things like that, you could run into trouble, also depending on your deployment model. So these add up to basically these 2 round trips going back and forth to retrieve this information. So what if we add in a query, an outbound query? We're going to go out that has chunk. This is like that first query. So here I've collapsed each round trip into just one line, but we say, does this vertex exist? It gets the edges, then it gets the first chunk's properties, so that first vertex, and it gets the second chunk properties, so that second vertex. So what can we do? So here's the first thing that you can do, the configurable thing. So with Titan 1.0, they've added this option in this query batch equals true. And so if you go into the Titan configuration and turn this on, what this is going to do is batch up Titan's request to Cassandra. So in my trivial little query where I'm actually only starting at 1 vertex, you're not really seeing the benefit of the batching up of the edge queries, but what you are seeing here is you'll notice that that last retrieval of that second vertices properties got collapsed into that previous request. So it was able to just go out, grab that, and pull it back. So that makes a difference right there. Now, what else can we do? Well, if you want to get extreme here, and I'll put a warning on this, just because you want to test out and make sure that this works right for your situation, but say you're very certain that that vertex with ID number 4 exists. So you better be very certain about it. It doesn't matter so much on the read side if it doesn't really exist, but if you do that, storage batch loading true, that's going to turn off Titan's internal check to see if when you give it a vertex ID, does that vertex actually exist in Cassandra? And so what happens then is you can just see we're down to basically the minimum number of queries that back and forth with Cassandra. We get the edges, and then we get the chunk properties, so 2 round trips. Okay, so that's on the read side. So let's look at optimizing on the write side. So one thing that we ran into when we were putting together this time series model was some issues with insert performance. And so here's just a really simple insert. Remember, I'm doing this sort of odd thing where I'm really just care about that edge. So I'm saying chunk add edge has observation, that's that label. I'm pointing it back to itself, for better or for worse. Adding in the timestamp property and then just a double value. Okay, so what does this look like? You could probably guess. With these settings off, does vertex exist? Then it writes a new edge. And so notice what happened here is we wanted to do a write, but we also introduced a read. So you can imagine as you scale this up, for it's potentially, depending on your load, as I mentioned, there's a transaction cache. If you're writing maybe to the same chunk over and over again in the same transaction, say batching up your commits, it doesn't make a huge difference. But in most cases, you're probably going to be writing across many different things, so many different sensors or data collection devices. Okay, so what can we do? Well, if we do storage batch loading true, then we get rid of that vertex exist query, and what we end up is with just this new write edge. And so what happens there is then your actual write is just writing to Cassandra. Felt like there needed to be some requisite flame graph in the presentation. So here's a flame graph, storage batch loading equals false. So that's what that vertex check in there. This is just a quick and dirty test I did over the past week just to get some numbers and examples. So that big chunk, I know you can't really read that, but that big chunk on the right is actually all those calls to get vertices. So spending a significant amount of that time of its insert actually pulling back and doing that read to Cassandra. So if we do storage batch loading true, that goes away. On the left, you can see that chunk is actually where the commits are happening. So all that stuff on the right isn't actually I/O anymore. That's just other things that are going on. So just, again, quick and dirty performance numbers. This is not supposed to represent any sort of definitive what sort of insert rate are you going to get out of this system. But for the sake of just giving you guys maybe some sort of rough order of magnitude on an untuned system, I set up a cluster on AWS, 9 M32X large nodes, Cassandra 2.2, replication factor of 3, writing a quorum, didn't do anything else with them. Set up one other node that was this client that was writing time series data, 100% write workload into this cluster, 10 write threads, committing, I think, 50 of these observations at a time across 100,000 different series. So you could think of that as 100,000 different sensors or something that you're writing data to. And so what happens at the beginning is actually, as I mentioned, the one downside is you need to manage these chunks that you're writing to. And by manage, in this case, what I mean is, well, when you get a new point in, you need to figure out what chunk am I going to put this under. So in maybe CQL terms, what partition is it going to go into? And so just in this quick test, we do some caching. So we retrieve that chunk once, and then we just have a very simple lookup that we do on our application side to say, give me the chunk back, so I don't actually have to go to Cassandra and look it up again every time I do a write. And so that's why it ramps up. And then we level out a little bit under 90,000 writes per second. But again, take this with a grain of salt. Just figured I'd put something up there. Okay, so in summary, Titan is a graph database on its own, but it's of course important to understand kind of what the implications are of how it uses Cassandra to help get the most out of Titan. One thing that we learned on the write path is depending on your needs, it could be good to remove some of those reads from your write path. Again, I put a warning up there. These are things that you want to try out on your own setups, see what happens. So it's not just a blanket, thou shalt go do this. One other thing I didn't mention is if you're writing large numbers of vertices, Titan has its own scheme for coming up with vertex IDs. And sometimes allocating these vertex IDs can be more of an expensive operation. So when a node runs out of vertex IDs, it gets an allotment and needs to get another set of vertex IDs, that can take some time. So here's two more parameters that you probably want to look at: an ID's block size and ID's renew percentage. Those are some things that you can tune to ensure that that wait time when that happens isn't too high. On the read side, I can definitely say, you know, query batch equals true is probably going to be helpful in a lot of cases. I mean, it sort of depends on what sort of traversals you're running, but it's probably worthwhile enabling that. And then lastly, of course, global and vertex-centric indices. We didn't really talk about the vertex-centric indices too much, but on that time series data, that vertex-centric index is actually ordering, allowing Titan to order that time series data in either timestamp, ascending, or descending order. So you have the power to do that. Okay, so that's it. I'd like to thank you all for coming. What sort of questions do you guys have? Mm-hmm. Yeah, so say you grab the edge. The edge has the IDs of the vertex that it's connecting to, and so it'll grab that ID and then do another query. Titan will do another query to look that partition up and retrieve it. Mm-hmm.
Anyone else have any questions?
Did you run into any sort of size limitations or in Titan as you explored different relationships and different vertices?
Like different, like vertex
Right.
counts or something like that?
Uh-huh.
No, we haven't so far. I know that there are graphs out there running in the tens to more billions. Ours isn't that size right now.
Right.
But yeah, we haven't run into one. As far as edge count, so specifically, if you think about a non-time series example, like if you're modeling a social network and you have somebody who's very popular, what we would call a supernode, and they have lots of edges going into them, Titan's going to have potentially the same sort of limit as the underlying layer of, you know, how wide can that row be in Cassandra.
Okay.
So.
So if I can follow up another question.
Yeah.
I can have a very rich metadata relationships modeled in Titan and then persist its key value pair properties in Cassandra.
Well, so Titan is actually storing its data in Cassandra. Okay. So
its own model it is storing in Cassandra.
Exactly. Yeah. So Titan doesn't have its own native storage. It's using Cassandra for that.
So how would I associate instance data that can extend into hundreds of rows or thousands of rows for that vertex on a time series? Say that if that engine or sensor has a vertex and then it has thousands of rows, how would I put that in Cassandra under that table or column?
Yeah, so you could either follow a model like I demonstrated here with Titan and actually store those as edges, or the other, of course, alternative would be, say, if you wanted to use Cassandra, just CQL, say, as your time series database. In that case, you could store, and a lot of people would do this, store that time series data totally separately, and then, of course, you maintain a reference between the two, but it's not a hard reference.
Okay.
Mm-hmm.
Okay.
Hi. If you don't mind, can you go over how Titan stores data in Cassandra once again?
Yeah. Okay. This one is that? Yeah. Okay. Okay. So yeah. So here, this example is a CQL schema for storing the sensor data. And so here, if you think about, and again, I'm kind of falling back on thrift terms here, but if you have your partition in Cassandra, and so it's going to be bucketed out by dates. So now if we flip over here, what's going to happen is we have our vertex IDs, and so think of that as the partition key. And then we have some arbitrary number of columns, cells, whatever you'd like to call them. And so what Titan's going to do is actually serialize those key value pairs out using its own serialization into the columns that are on that partition. So we're going to start, we have properties there, so if the name's actually on the vertex, that's going to be first. Then following that, possibly in order by some key that you've set up in Titan to be a vertex-centric index, you're going to have your edges. Exactly, and in this right here, they technically could be going in or out. And you could walk that from either direction. So in my little query examples, I always said out, but you could say in, and depending on the direction. And then the edges themselves, that's the basic format that it's packing that information into the edges.
Then I would store the instances of the time series.
You could go either way. Yeah, it's just going to depend on what makes more sense, what sort of performance requirements you have. Yeah. Mm-hmm. Yeah. So Titan has some sorts of schema definition, but it's not schema definition in the context of setting up, say, a table and saying, you know, table person has these 3 columns. And so in Titan, what you do is you can say, for this particular property, take like that name property I had on that vertex. I'm going to say name is always a string. So you could say something like that. So you'll define that in the Titan type system. You won't say a person has a name, a date of birth, you know, whatever it may be. So say you come down the road and you add some new property, say address. So you go in, you define what is the type of this address property, but then you can go and add that to whatever vertex that you would like to. And so what's going to happen ultimately is that data will be stored as a property along with that vertex. Yeah, that's a good question. So the other thing that you can do while you're creating that type is actually set up indexing on it. And so there's 2 kind of basic types of indices with the graph database. One is that global index. Like if I'm looking at all the vertices across the whole graph, and I want kind of, if you remember my query, it started out with, I want all the people named Ted. And so it's from that level, I want to dive into the graph and just grab those. And so with that, you actually have 2 different options. You can either use Titan's internal indexing system on that property. In that case, it's quick and efficient, but it only supports equality type checks. Now, if you want something else that supports a more robust type search query language, you could use something like Solr or Elasticsearch. And so when that property gets added in, it'll be indexed either by that Titan indexing system or that third-party indexing system that you've set up. Yeah, so if you're in a situation like that, like in the Timeseries one, you can kind of think, okay, well, I can put some sort of arbitrary time range boundaries on this or something like that. So oh yeah. So he was wondering about in the situation, like I mentioned, we were talking about the supernode, say in like a social network. type situation. Oh,
I have a question actually regarding the Titan setup. Like when you're installing, it has to be in a standalone machine, or it can be a part of the Cassandra cluster.
I'm sorry, can you say that one more time?
So the Titan as such, can it be a distributed machine, or it can only run on a standalone machine?
It can actually run on the same instance. It can run on a different one. You could have a one-to-one match between Titan and your Cassandra nodes, or you could have less Titan nodes. So there's a lot of flexibility there, depending on how you're using it. So it doesn't have to be set up directly on the box or off. As I mentioned, of course, because it is communicating and has its own communication pattern with Cassandra, there could be implications of increased latency when you move it off the box. Having said that, depending on what your application's doing, there could be garbage collection, contention type issues. If it's running in the same JVM, you may need to tune that more. So there's trade-offs with the different approaches.
Okay, so what do you suggest, like one machine or in multiple?
It really totally depends on your workload. Yeah.
Okay. Okay.
Yeah. So
Yeah, so my question was basically regarding the supernode. Just like what kind of modeling technique would we use in Titan to kind of not reach that situation?
yeah, so say you reach like, I don't know, like 1 million or 2 million edges or something like that hanging off of a vertex. So you would have to, if you're starting to run into issues or think you're going to run into issues, you're going to have to split that vertex somehow. One thing that I think probably they may go over tomorrow, but there's a Titan 1.0 presentation tomorrow. But one thing that Titan supports, and I didn't cover it all here, is vertex and edge partitioning. And so what that means is Titan can actually partition vertices and or edges across your cluster. So that may be one option. If you check out the Titan docs, they have a lot of really good documentation. I should say in general, the Tinkerpop docs are really good too, lots of good examples. But you can read more about that partitioning. The other option would be if you somehow in your modeling strategy come up with some at least maybe semi-logical way to say, well, I'm going to split this out into these two separate vertices and then handle that in your application logic. But
so Titan would be taking data from Cassandra and duplicating it.
no, actually, all of the data stays in Cassandra. So if you think about MySQL and how they have, you could choose to use, say, InnoDB or another storage layer, but MySQL would be running the query optimizer, things like that. It's somewhat similar to that in that MySQL, say the query engine is not actually storing any data, but InnoDB is. So this is a similar case. Titan is maintaining caches. It's doing query optimization. It's implementing this graph abstraction. It's taking care of all the serialization, deserialization to Cassandra. But all that data is living inside of whatever storage you chose to put behind Titan. So Titan itself sits on top of that underlying data store.
If you can go back a couple more slides to the different things that connected
This
to
way?
it. Yeah. There.
Aha. Okay.
So is that the whole list? Like, is there like a PHP and umpteen other things, ways of connecting to it?
I don't think there's a PHP one. I would not consider this list exhaustive or authoritative. That was me on the wild, like Google image search thing. So I'm not. I don't think there's a PHP one. There is one. Sweet. There is a PHP one. Yeah. There's also, I didn't mention them here, but there's also object-to-graph mappers. So similar to an ORM, but it's an OGM. And so there's a number of those out there for different languages. Java, Python has a few. So that's another option if you prefer that. Okay. Oh.
So just a question on kind of how Titan is interacting with Cassandra. You're saying it's using the Thrift protocol to kind of talk to it.
Yes.
And my understanding is Thrift is being deprecated. So have you seen any issues kind of like, work, kind of the interaction between Titan and Cassandra? Because it's 1.0, and I'm assuming, is there like a version coming out that would not use Thrift going forward?
I think there had been some work on a CQL adapter, but I'm not sure where that's at. We haven't had issues upgrading Cassandra behind Titan so far, but no, I mean, that's a very good point. I'm not quite sure what's going to happen with that in the future, but thank you.
Thank you very much.